that we described was we've got a list of some number of classes, of object classes. And we have an inheritance map of which classes inherit from which other classes. So this is the sample map they gave you where class D inherits from both class B and class C, and both class B and class B inherit from class A. And so we had some input limits. Some of the input limits that they gave you on how big this is going to be is, for the small case, there's no more than 50 classes. For the large case, there's no more than 1,000 classes. And importantly, and a lot of people miss this, in both cases, each class can only inherit from at most 10 other classes. Okay? So the first question I asked was, how can we represent this inheritance structure as a graph? What are the nodes going to be? What are the edges going to be? And it should be pretty straightforward just from looking at the diagram. The nodes are going to be the classes, and we'll point an edge from a particular class to any class that it inherits from. So this is the graph that represents the sample problem. And then we talked about a couple of different ways to classify graphs. So I talked about 4 different distinctions that we can make on graphs. So is it directed or undirected? Well, remember, a directed graph has an asymmetry in the relationships that the edges mark. And so this is clearly asymmetric, so this is a directed graph. Is it weighted or unweighted? Question there is whether the edges are Boolean or whether there's some numerical value associated with them. And if a class inherits from another class, it either does or it doesn't. There's no degree of inheritance. So this is an unweighted graph. Is it simple or non-simple? And remember, if it's non-simple, that means it either contains a self loop, where a class has an edge connecting to itself, or a multi-edge, where there's more than one edge between any 2 classes. And if you read the input statements, the description of what the graph is going to look like, both of those are explicitly excluded. So it explicitly says you can't have a class can't inherit from itself, and a class can't inherit from the same class more than once. And so that makes this graph a simple graph. And then finally, is it cyclic or acyclic? And so a cycle, remember, is a path in the graph from an element that points back, that goes back to that element. So we're told in the input statement that if there is an inheritance path between 2 nodes from x to y, that there can't be an inheritance path from y back to x. And that's equivalent to saying that there are no cycles in the graph. So we have classified our graph as directed, unweighted, simple, and acyclic. And then we can use those properties when we go on to do more analysis. And everybody did fine on that. Okay. Part B was actually the place where actually I think nearly everybody made the same error. So what I asked you to do in part B was compare the maximum number of vertices and edges under the small and large input limits, and see how that changes the memory footprint of using an adjacency matrix versus an adjacency list to represent this graph. So the vertices are straightforward. So vertices under small and under large is the maximum is 50 for the small case and 1,000 for the large case. The place where a lot of people made an error was in calculating edges, and that's because they didn't read this statement. So if you read in the input limits, every class can only inherit from at most 10 other classes. And so a lot of people skipped that and said, okay, in the large input limits, you know, each of these could be potentially connected to every other one, so there's 1,000 squared possible edges, and that's far too big. This is a sparse graph. So at most, we can only have about 500 edges for the small case and about 10,000 edges for the large case. which is much smaller than if this limit wasn't here. Under these limits, then an adjacency matrix requires v squared space. So for the small, so if we're using a matrix, for the small, or let's look at for the large. So for the large case, that's going to require about 1 million possible spots. So 1,000 squared, because you've got 1,000 by 1,000 matrix to hold all of the possible edges that could be there. And if we choose a list, that takes v plus e space. So we have only about 11,000. So we've got about about 2 orders of magnitude less space for the adjacency list. And again, that's because of these limits that guarantee that the graph is sparse, that there's not very many edges compared to how many total possible edges there might be. And that's usually the case for most problems. Most graphs you're going to work with are fairly sparse, which is why I recommend using a list. OK. So once we've done that, then I asked you, what would a graph traversal look like on a directed graph like this? So if we start from a particular vertex, which other vertices are we going to reach? So suppose we pick as our starting vertex, vertex C. So we start at C. What's the next vertex we're going to get to? A, right. We're going to get to A, and then what else? Nothing else. That's it. So the only things we'll traverse if we start from C and go to A are 2 vertices. We're not going to get to B and D. So the only vertices we're going to reach when we start from a particular vertex are those that are ancestors of our starting vertex. So in this case, C inherits from A. A is an ancestor of C. So when we traverse the graph starting from C, we'll get to A. What happens if we traverse the graph starting from D? Well, we'll start off by going to C and B, both of which are direct ancestors. And then each of these leads us back to A. But we get back to A twice. So A shows up as an ancestor of D multiple times. And that's exactly what we're looking for. If we see multiple paths in our traversal from our starting vertex to our ending vertex, that means there's a diamond inheritance here. So the way that we can write our code to do this is like this. So remember, we're going to keep a visited array and then a list of available vertices. So we're going to start off at D and mark D as visited. So this is now true. And then we will say, OK, we've been to D. Now we can get to B and C. And then we visit B. That's true. And then we add on, now we can go to A. And then we visit C. That's now true. And then we add on another A because there's an edge from C to A. And then we visit A, mark that as true. And then we try to visit A again. But A is already visited. That means that there's at least 2 separate paths to get to A from D, which tells us that A and D contain a diamond inheritance. So that's how we would find all of them. And most people got this. The major error that I saw in this is that when you're doing these searches to look for diamond inheritance, you have to start from every possible vertex. Because if you don't, you might miss some. So in this case, if we only started from C, we wouldn't find any diamond inheritance, and we would erroneously return false. There's not one here. Because it only shows up if we start from D. So we have to go through all of the possible starting vertices, do our traversal, look for trying to hit something we've already been to, and then return true if we find that. All right? So that was the homework. Great job on everyone who got that done. And let's move on to more graph stuff. All right. So last week, we kind of introduced everyone to graphs. We talked a little bit about how to translate problems into graphs. And then we talked about these graph traversal algorithms, the breadth first and the depth first search. So today, now that everybody knows everything about graphs, we're going to start covering basically as many graph theory algorithms as I can. If I'm going too fast, please interrupt me, ask me to explain. I'm trying to go as fast as I can while still explaining things properly, because there's a ton of interesting algorithms that I want to cover. OK. So let's start off with some ways that we can use the graph traversal algorithms we talked about last week in some ways that might not be immediately obvious. So here's a graph that I already drew. And this is related to the one that I was using last week. So we've got the nodes are the numbers from 1 to 7. And this is an undirected graph. So one problem that you'll see a lot is if you want to know if a graph is connected or not. So and connected means that there's a path between different components. So if a graph is disconnected, you can pick two vertices in the graph, and there's no path between those vertices. So in this case, this is disconnected because 1 and 7, or 2 and 6, or whatever, there are some pieces of the graph that there's no path to the rest of the graph. So in particular, this particular graph has two distinct connected components. So each of these subgraphs that is connected is called a connected component, and there's two of those here. So a common problem you will see is identifying whether a graph is connected, and if it isn't, counting the number of connected components. So how can we use a graph traversal algorithm to do this? Anybody have any ideas? Yeah.
Do you try to like pick a random point and do like a breadth first search on it?
Yep.
And, obviously there'll be some things
Yeah, so we pick something at random, say 5. We do a graph traversal starting from 5. And from that point, we'll get everything that's connected to 5. So if we do a graph traversal from 5 and mark that as visited, then now, OK, we can get to 4, we can get to 1, we can get to 2, we can get to 3. We can't reach these. There's no way to get there from 5. So we've marked now all of one of our connected components. And then we just go through our list of vertices and say, OK, is there one that we haven't reached yet? And there is. So then we repeat it. So now we say we pick one of the remaining vertices that we haven't been to. Maybe we want to start at 7 and do a graph traversal starting from 7. And then we reach 6. And now we've been everywhere. And we've marked each of the vertices with the component that it's from. So these are the red vertices. These are the green vertices. So there's two separate connected components. So one particular instance of this problem that's very common if you're working with image data. It's called the flood fill problem. And so usually what you're working with is a grid of pixels or a grid of something, where the question is, OK, how many white regions are there on this grid? How many distinct white regions that aren't connected by white pixels are there? And so we can model this with an implicit graph. So we can treat each pixel as a node, and there will be an edge between pixels if the pixels are next to each other and if they're the same color. OK? So what happens if we start from this corner? What pixels are connected to this one? Well, it's this one and this one, because those are both white. So then we can color those the same color. And now here, there's no more pixels connected. And now here, there's no more pixels connected. So we've flood filled in this particular region as all being pixels that were connected to each other. And you can do the same thing with these other regions. So we pick another white pixel, mark it as red. Look at its neighbors. This one's black, so it's not connected. This one's white, it is connected. We fill it in, fill it in, fill it in, and you get that region. Just by doing a search, either breadth first or depth first search, on some pixel that's a part of that component. And so you can do that and say, there are 3 distinct white regions of this image. So this is exactly what happens anytime you open up Paint on Windows and you do the paint bucket. On a pixel, it's doing a flood fill from that point using this algorithm. OK. So those are kind of more basic stuff. The other basic thing that I mentioned last week is the shortest path on an unweighted graph. So if we have an unweighted graph and we want to know, OK, what's the shortest path from 1 to 4? Because we could go through 1, 2, 3, and 4. We could go 1, 2, 5, and 4. There are a bunch of different paths. Which one is shortest? And you can find a shortest path by doing a breadth first search from your start vertex and looking at how many hops in your breadth first search it takes to get to your target vertex. So in this case, the first level of your search from 1 would be 2 and 5. And then in the second level, you get to 4. So this is 2 edges away. All right? I will get to what you do later when these edges are weighted. All right. So let's talk about another problem. And I mentioned this last week as an interesting one. So let me draw a directed acyclic graph. So G, A, B, C, F, D, F. B2D, B2D, and C, F, and B2C. All right. So here's our graph. The nodes are the letters from A to F, and all of the edges have a direction associated with them. So when I talked last week about directed acyclic graphs, I said that they were really useful for modeling sort of priority problems. So maybe each of these is a job that you have to do. And the edge says, OK, before I can do job A, job G has to be done first. Something there is required in order to do job A. So the classic problem on directed acyclic graphs like this one is to come up with a topological sort of the graph. And a topological sort of the graph is an ordering of the vertices so that every edge in the graph points from an earlier vertex in the sort to a later vertex in the sort. OK? So if we sort of flatten this and organize the vertices so they were all in a row, every edge would point from left to right. There wouldn't be any edges going from right to left. So as long as the graph is directed and acyclic, there is always at least one topological sort. Sometimes there's more than one, but you can always find one. And the reason why we might want a topological sort, there's a couple of reasons. So first of all, if it really is sort of a task priority description, then a topological sort gives us a feasible order in which to do our tasks. So if we come up with a way in which all of these edges are pointing to later, then we can just process our jobs in that order, and we are guaranteed that by the time we get to each job, all of its prerequisites will be finished. The other thing that's useful about this is suppose we want to do maybe some path searching from some node in our directed acyclic graph to some other node. which nodes do we, or which vertices do we have to examine when we're doing that? Suppose we've sorted everything topologically, and we have some node x and some node y. So we've got our list of nodes in topological order, and we want to find a path from x to y. Which nodes do we have to examine to look at that? Well, so all of these that come before x in the sort, there's no way to get to those if we start at x, because again, all of the edges are pointing right. There's no leftward edge to get back here. So we can exclude all of those. They're not going to show up in any path from x to y. What about all of these down here? Well, if we end up down here, there's no way to get from here back to y, so we can't end at y. So these are not going to show up in a path from x to y. So we can only have to examine a particular subgraph in order to find any particular path between any 2 points. And so if that subgraph is much smaller than the larger graph, that can be a big gain. Because topological sorting is fast, if we're looking at a lot of paths, then we can use that sort to really constrain our search. All right.
What's the runtime of topological sort?
What's that?
Is it n log n?
I'll get to that when I finish the algorithm description. OK. So how do we find the topological sort? Well, so we can note that every vertex has some number of incoming edges. Those note vertices that have to be done before it, and some number of outgoing edges, which note vertices that have to be done after it. So the first node in our sorted order has to be a node that has no incoming edges, that doesn't have any prerequisites. So with that insight, let's go through our graph here and make an array that counts how many incoming edges there are for each vertex. OK? So we'll start at A, B, C, D, E, F, G. What's the incoming count for A? 1. And for B? Next. 2, 2, 2, 2, and 0. OK. So we've done our count. Now we go through and we find any of them that are 0, we put into a priority queue. Or some, sorry, that should be G, into some structure that we can pull out. These are valid, these are things that have all of their prerequisites filled. So these are things that can go next in the order. So right now there's only 1. So the first element in our sorted order has to be G. And now what we can do is go through and say, OK, G is done. We don't have to worry about those edges anymore. Those edges are completed now. So we mark those edges out on our graph, and we decrement the counters corresponding to those edges. So G pointing to A is finished, so we can reduce this A down here to 0. G pointing to F is also finished, so we cut this count down to 1. And now A has no edges coming into it anymore. So A is our next count. And then we reduce C and B. So we have 0 and 1. So the next element must be B. And then we go on and reduce C and D. 0 and 1. So now we are at C. So we go to C. We reduce F and E. We get 0 and 1. So F is next. We go to F. F points to E. So we reduce E, which is now 0. So we go to E. And then finally, we go to D. All right? So this is our topologically sorted order for this graph. We start at G. We go to A, B, C, F, E, D. And if we process the nodes in that order, every edge is going from an earlier vertex to a later vertex. And this is how we construct it. And we can construct it in time linear to the total number of vertices and the total number of edges. All right? So it's actually faster than n log n time. Alrighty.
It's not faster than log n time if the graph it has an edge from everywhere to everywhere.
In a sparse graph. In a sparse graph, which is practically all you're going to have to deal with. All right, so that's topological sorting, and it is very useful. It's the canonical problem on graphs like this. And if you look at any sort of graph package, there's a ton of them out there. Most of these algorithms are going to be implemented. So very often you won't have to go back and implement them yourself. It's more important that you know how they work, you sort of know their time complexity, and you know when you might want to use them. So by all means, try and implement a topological sort, but you can go and look in the NetworkX package, and that has a topological sort. Yeah, I saw you were using that. You can find these elsewhere as well. OK, so next problem. Let's draw another graph. This is going to be a weighted graph. So we'll have 0, 2, 3, 4, dot, 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 dot. And these weights will be 4, 4, 2, 8, 6, 6, 9. OK. This problem is called the minimum spanning tree on a weighted graph. What's a spanning tree? A spanning tree is a subset of edges that are in the graph that connect it. So some group of edges in the graph such that every node in the graph is connected to every other node in the graph. All right? So it should be clear that there are more edges than we need here to connect it. We could remove this edge between 0 and 2, and 0 and 2 are still connected because they can go through 1. So the question is, which edges can you pick? So if the graph was unweighted, it wouldn't matter which edges you picked. You could just remove edges that didn't disconnect the graph until you had the minimum number, and then that would be as small as you can, because the minimum spanning tree always has the same number of edges. There's n minus 1 edges. But if the edges are weighted, like in this case, what was this one? This was a 4. Then not all edges are equal. And we want to find the smallest value edges that still connect the graph. So this might be sort of the classical cases. These are cities, and these are the costs of building roads between cities. How can we build the roads with the least cost that still make it possible to drive from every city to every other city? OK? That's a sort of thing where you might want to start with this problem. OK. So suppose we have a list of all of the edges in the graph, sorted from smallest to largest. So let's come up with that. So there's an edge 2. That goes from 1 to 2. There's two different edge 4s. One goes from 1 to 0. One goes from 0 to 2. There's two different edges of weight 6. One goes from 0 to 3. One goes from 0 to 4. There's an edge of weight 8 that goes from 2 to 3. And there's an edge of weight 9 that goes from 3 to 4. So here's all of our edges from smallest to largest. How might we use this to decide what to do? Well, let's start off and just add the smallest edge. So we'll mark that in as red and say, OK, we'll add that edge. Let's look at the next one. So that's a go. We'll add 2. Then let's look at the edge from 1 to 0. Now, we only want to add the next edge if it increases the connectivity of the graph. So if 1 and 0 aren't already connected, then we want to grab the cheapest one that connects them. But if they are connected, it's a waste of time for us to add a new edge because that's not helpful. We've already connected them. We don't need it. So in this case, what we want to say is, OK, for 1 and 0, are 1 and 0 connected by red edges? Yes or no? No. So we'll go ahead and take that. That's going to be part of our minimum spanning tree. Our next one is 0 and 2. Are 0 and 2 connected by red edges? Yes. So we don't need to include that one. So then we go to 0 and 3, and that's a new connection. Then we go to 0 and 4. That's a new connection. And then we go to 2 and 3. That's not a new connection. 2 and 3 are already connected, and so are 3 and 4. So we've constructed a spanning tree that covers all of the nodes, but leaves out the edges that we don't want. So these are the most expensive edges that we can throw out and have the total cost of this spanning tree be as small as possible. This is called Kruskal's algorithm. And it depends on a fast way to tell whether two different edges or two different nodes are already connected or not. Anybody suggest, from our data structures lecture, a good way to do that?
A Boolean array to a tubular array. Actually, one is enough. True for if it is already in the spanning tree, false for not, and then every time you check the two vertices, you can.
OK, that would work. I was actually thinking of something different.
Oh, yeah.
What's that? Min heap on what? Keyed on what? So that might be a way to go through here. I'm asking, what's a fast way to tell whether two nodes are connected or not? Yeah?
Can you use a union find?
Yes. That is actually what this problem is what union find was developed for. Does everybody remember the union find structure? Union find supports two methods, one called find and one called union. And find on X says what group is X a part of. And union on XY says I want to put X and Y in the same group, so that merge the groups that X and Y are part of. So you can do exactly this problem. You start off with all of your nodes in separate groups. Every time you add an edge, you union the nodes that correspond to the ends of that edge. And you can test whether they're already merged or already connected by running find on each of them. And if they come out the same, they're already connected. We don't need the edge. All right? So again, this is a minimum spanning tree. This is called Kruskal's algorithm. And there are alternative algorithms, but this is the one I like best. So that's the one I'm teaching. OK. And the time complexity of Kruskal's algorithm is about E log E. So it's very fast for sparse graphs, particularly where the number of edges is fairly small. OK. So we talked last week about shortest paths on a weighted graph. So let's talk about shortest paths on an unweighted graph. Let's talk about shortest paths on a weighted graph. So let's draw another pretty graph picture. 3, 2, 1. So that's going to be here, 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 here. And we'll draw in the weights in a different color so it's easier to see. This is weight 1, weight 6, weight 5, weight 3, weight 2, weight 7, and weight 6. So on a weighted graph, it's not as strict. We can't just use a breadth-first search to find the shortest possible path, because what a breadth-first search does is finds the path with the fewest number of edges. And so it might find a path that has 2 edges of length 10 and length 15, whereas there might actually be a shorter path with 3 edges of 5, 6, and 7. And so we need an alternative way to do that. And so what I'm going to show you is called Dijkstra's algorithm for shortest paths, named after a Dutch guy called Dijkstra. So it takes a starting vertex and it will give you the shortest possible distance to every other vertex. So we'll start with two data structures. We start with an array D that contains the distance from our starting vertex to every other vertex. And we're going to start from vertex 2. So we'll have index 0, 1, 2, 3, 4. And so we know that the distance of 2 to itself, the minimum distance is 0. So we'll just fill that in with 0. And all of these other guys we'll set to the maximum integer, something big, so that we can quickly replace those with smaller values. So we'll just call that m for something big, max int. And then we'll keep a priority queue. We'll call that p. And that's going to contain pairs of distances to x for a particular vertex. And we'll initialize p. And this will start off as containing just 0 and s, because that's where we're starting with. We're starting at vertex s, or sorry, starting at vertex 2. And the distance of 2 to our starting vertex is 0. All right, here's how this algorithm works. We remove the minimum item from our priority queue. In this case, there's only one. And then we relax all of the edges from that vertex. This is what relaxation means. So we're going to explore every edge. Let me write in what we've got in our distance array right now. So this is distance 0. So we remove the minimum distance pair from D. If that D is larger than what's already in our distance array, then we already know a better path there. So we don't have to worry about this new potential path, and we just skip it. But if it's not, then we need to go through these edges. So we know that there's paths from 2 to 0, 3, and 1 of distance 6, 7, and 2. So if we travel through vertex 2 to vertex 1, or vertex 0, that distance is going to be this 0 plus this weight 6. So that will be distance 8 to get there. And we can go in and look up here and say, oh, is 8 smaller than the best current distance we have so far? Yes. So we'll fill that in as 8. And then we push that new pair onto our queue. So we add on 8, 0. And then we do the same thing for these other ones. So we get a distance 7 here. And yeah, I'm sorry. You're absolutely right. Distance 6. My bad. So we've got 7 and 1. And then our priority queue, we pushed on, 6, 0. We pushed on 7, 3. And then we pushed on 2, 1. And these are ordered by distance from the current vertex, or from the target vertex. Yes, that was correct. OK, so then we remove this new first element. Now we're going to go to vertex 1 that's distance 2 from the start vertex and go and look at all of its edges and say, OK, can we do any better? So, all right. We can go from 1 to 4. That's distance 6. And 1 is already 2 away from our start vertex. So this has a new distance of 8. So we can fill that in as 8. And if we go on this path, now if we start from here and go to 3, this edge has weight 3. And it cost us 2 to get here. So we have a new, shorter path of length 5. So we can go in and update our distance array to 5 there. And so we've removed this, and we've changed two values. So we update this with, let's see, 8, 4, and 5, 3. All right? And then, so this is the new shortest distance. So we go up here and say, OK, we know how to get to vertex 3 with a distance with only 5. So let's look at all of its edges. Is there a shorter path anywhere? Well, we could go from here to 4. That costs us 5 to get here, and 5 to do the hop. That's 10. That's not any better. So we'll leave it as it is. We could go back to 2, but that doesn't help us. We could go back to 1, but that doesn't help us. So we're done. We can't get anywhere else from there. We could go now to here and say, all right, is there a shorter path anywhere? Well, from here, we could go to 4. It costs us 6 to get here, costs us 1 to travel this edge, and that's 7, which is shorter than the current path to go here. So we can improve ourselves by going from 2 to 0 to 4 instead of the current path, which is from 2 to 1 to 4. So we'll update our value here, and we'll push the new value, 7, 4, into the queue right here. And then we will walk through all of the rest of these, and we'll find that none of them give us any updates. And so this is our optimum distance array. And anyone like me to go through that a little slower? I know it's a little complicated.
So you visit every node from every node. So, like,
Yes.
traverse the graph from every node. So
You're traversing the graph, and you're traversing every edge in every direction, and seeing whether traversing each edge in any direction improves the current best option that you've found so far. And at each point, you're going to the closest node that hasn't been fully explored. So that's what this priority queue is telling you. Because you want to sort of move out in increasing distance from the source vertex and explore everything. OK, so that's Dijkstra's algorithm. This takes roughly v squared time. Yeah?
Is this for directed graphs or undirected graphs?
So you can use it for either. It will work for either. So in that case, some of the distance arrays might be left at max int, and that will be if there's no directed path to get there. So otherwise, it should work just fine. The case where you do need to be really careful with shortest path algorithms is if you have negative weights. Negative weights can screw up your algorithm. And in particular, if you have a negative weight cycle, you can have some really weird problems. So suppose that this edge from 4 to 1 was -9. What's the shortest path from 2 to 3?
I was thinking of something else, but it's now going to be -9, right? And then, like the shortest path from.
Well, so we could go from 2 to 3, and that's -9. But we could also go from 2 to 3, and then from 3 to 1, and then from 1 to 2. That adds 5, so that costs us -4 to get from 2 back to itself. And then we could go back to 3, and now we've got a cheaper path. It's -13. We could go through this cycle however many times we want and get as low of a value as we want. So you have to be really careful with negative numbers. What this called is a negative cost cycle that can cause those problems. And in that case, anything that can go through the cycle, there's no defined shortest path. All right? Makes sense? So again, that's called Dijkstra's algorithm, which is one of the standard ones if you want to look it up in your textbooks. There are other shortest path algorithms that will work a little better on negative weights, but usually you don't see them. So it's generally not a big problem. So I think I'm about out of time here. Let me see. Yeah, OK. So I don't really have time to go through everything else interesting today, because I want to give you some time to go over the homework. some graph problems and algorithms that you might find worthwhile looking up. They're interesting. Floyd-Warshall's algorithm is a modification of solving the shortest path problem that takes 4 lines of code. And it's a bit tricky to understand how it works, but once you understand how it works, it's very fast to implement, and it's useful in a lot of situations. And in particular, so this problem told us what's the shortest distance from vertex 2 to everywhere else. Floyd-Warshall's actually gives you the shortest path from any vertex to any other vertex. So if that's the problem you need to solve, that might be worthwhile. Prim's algorithm is an alternative way to do the minimum spanning tree. Again, I showed you Kruskal's algorithm because I like it better, but there are some situations where Prim's is better. Learning how to do maximum flow problems, which I really wanted to get to and I just didn't have time. So that might be on a weighted graph like this, where now these edges might represent the capacity of stuff to travel from one vertex to the next. From a start vertex to an end vertex, find the maximum capacity that can flow along those edges. And so that is another useful problem that you can see a lot. And so, again, graphs are fun. There's a lot of interesting problems out there. And generally, the biggest thing that you really want to work on anytime you get a problem that might be able to be solved with graphs is figure out the best way to model it as a graph. Because generally, there's a ton of good algorithms out there to solve that. You're not going to have to come up with a new algorithm very often. Really, what you need is the best way to model your problem as a graph. All right. So this next homework assignment is going to be a little different. There is no class next week because of fall break, so we will not be meeting next Friday. And because of that, you've got an extra week to work on your homework. It's not due next Wednesday, it's due the Wednesday after that. So you get a week and a half. And I see smiles out there. I think everybody's got midterms right now, so hopefully that will lower the stress a little bit. But do go ahead and take a look at it today, and we'll walk around and see how it goes. All right.